So thank you. Thanks to Murat for organizing the conference and for everybody for attending. I know this was actually probably the most challenging weekend of the year to get to Albuquerque. I myself flew in, my plane was 6 hours late, so instead of landing at 10 o'clock last night, I landed at 4 a.m. Last night, which was always fun. The good thing is I got to say good morning to my kids on my way to the hotel, so that was fun. So anyway, thank you for being here. And yeah, the conference, it's really exciting. It's nice to see how this has grown over the past few years. And I think this is going to be our best year yet. So thanks to all of you. So Murat asked me to present a few slides, and I'm going to go in the opposite direction of Dan. I'm going to have slides with very few words, in part because we have an active solicitation on the street, and I'm not allowed to say too much that might be construed as, modifying what's in that solicitation or otherwise informing that solicitation. So I just want to say sort of broadly what I think are the directions that are likely to be the most profitable, the sort of three different approaches that I see for making significant advances in neural computing. I'm going to take for granted, as Dan said and as others before me, that we really need to be looking to neural computing or to the brain to make significant progress in computing over the next 10, 20 years. I buy all the arguments that, not quite that Moore's law is dead and that we're out of ideas there, but that we need something new on the horizon to take us in a different direction than what we've done today with stored program logic and von Neumann machines and so forth. And so I think as we think through how to make advances in neural computing, given that we have to make advances in neural computing if we're going to advance computing in general, I think of sort of three general categories. And so the first, these are all labeled things that start with I because I'm a sucker for alliteration or whatever. So the labels are not perfect. But, and the first is engineering innovation. So by this I mean devices, new device physics, new things like memristors and spintronics and things that really we can use at the level of the silicon or at the substrate that will enable us to make significant advances towards not just more neural-like algorithms, but more neural-like efficiencies. Because one of the things that, when we talk about neural computing, we talk about all the fancy things that our brain is able to do, one-shot learning, of course, and many other cognitive perceptual tasks. But there's also this massive power imbalance between the amount of power it takes for our brain to do these computations and the kind of power it takes currently in the rack systems and GPUs in the server farms that are running the things that are arguably the production things that are the closest to neural systems today, which are deep neural networks. We're in the brain, we're on the order of 20 watts. GPU is, even a single GPU is, 5 or 6 times more than that. So to get down to the kind of computing efficiencies that the brain affords, I think we need to make significant progress in the engineering on the device physics level. And Dan is doing a lot of that in his programs. In Upside, for example, which I think there are a number of performers here or people who are related to that program who will describe their advances on that approach. And I think that's a profitable direction for research. The second sort of category that's on this slide is human intuition. And, I couldn't think of the right label for this, but basically this is the idea of saying, let's imagine for a moment that we don't really want to even claim that we have an idea of what the brain is doing, or that we really understand what the important parts of what neurons are for computation. And let's assume that we don't have exactly neuron-like entities available in hardware, but we have a bunch of sort of neural facsimiles that do things like spike or share other properties in common. The question for this category of research is, can we take those neuron-like elements and just use our human intuition and creativity to come up with fundamentally new or fundamentally more advanced paradigms for computing? And a good example of that, I think a good example is deep neural networks, right? Deep neural networks have, in the end, very little to do with the way that the brain is probably operating. And yet, they are incredibly effective at a whole class of problems demonstrated most recently over the past 2 or 3 years, as Dan showed in the image processing and object recognition. But this is a class of algorithms that really, again, it's based on our human ideas of what we could do with a neuron-like computing element, not necessarily on what the brain is doing with neuron-like computing elements. I think there's a whole new opportunity space that's opening up here in the level of hardware. Historically, neuromorphic computers were on the order of thousands of neurons per chip. And in part propelled by investments by DARPA and the Synapse program and other investments in this space and the work at the EU, we now have systems like the True North system, the Spinnaker chip, the BrainScales project, where we have millions or even more, tens of millions of neurons available on a single computing substrate. And again, whether those neurons are meaningfully similar to biological neurons, I think, is a somewhat secondary question. I think for this lane, this human intuition lane, the question is, now that we have a million entities on a chip that are not a stored program architecture, that are not a von Neumann architecture, that do not use digital logic, can we do something, or do not rely on standard logic computations? Can we do something interesting with those neurons? Can we build new applications out of that substrate? And I think we're just starting to see what we can do. There was a really interesting paper in Archive a few weeks ago that probably many of you saw called Neural Turing Machines, which was showing how you could actually train deep neural networks with long short-term memories to essentially perform algorithms, sorting algorithms, and other sorts of adding, multiplication. And again, that's a different computational structure for doing math things that we care about that may have nothing to do with how the brain works. Now, the third approach that I wanted to highlight on this slide, I'm labeling biological inspiration. And really this is to say, basically, we don't know, like Dan said, we don't really know what the brain is doing. We know what neurons do for the most part, but we don't really know which part is important, right? We don't know how much of what neurons do is related to biological equilibrium processes, how much of it is sort of artifacts of evolution, how much of it is really important for any given computational problem. Neurons can be infinitely complex computational devices if you include all of the nonlinear dynamics at the spine necks and at the dendritic trees and all of the sort of biological processes, the ion pumps and everything that keeps the neuron intact. But that doesn't mean that those are important for the kind of computations that we care about when we think about what the brain is doing. And so I think if we're going to rely on an argument that we have, there's a way forward because we see an existence proof of the brain, which is, as Dan said, I think that to credibly claim that, we can't just say that today we know what the brain is doing and go off and build it. We really need to go collect new data about how the brain is working. And I think we also need to develop new theories about how the brain is working, or at least enhance our existing theories. And so, we have, as I mentioned, we have at IARPA a program that's active now called Microns, Machine Intelligence from Cortical Networks, that is really trying to attack this third lane of potential innovation by combining new and existing theories of cortical computation, informing those theories with a set of large-scale data collection at the scale of neurons and of networks of neurons of thousands or tens of thousands of elements, and using the insights that we find in the brain to inform the next generation of computations, which may also inform the next generation of hardware, right? Before we go out and build that next chip, maybe we'll discover that for a certain class of computations, there's a certain feature of the neurons that's critical for efficient computation, and we want to make sure we build that into our hardware and don't just guess at it or over-engineer the system to include features that we don't need. Now, I think there's a clear challenge with this last biological inspiration approach, besides the fact that the slide doesn't show, and that is that this is not a new idea, right? So we had a nice talk at this workshop last year by George Dyson showing how even in the formulation of the EDVAC, John von Neumann, the godfather of digital computing today, or von Neumann architectures, drew inspiration for his machines from computational neuroscience and from the brain, right? At some level, he thought that he was building a system that worked like the brain, and now we sort of hold that up as the opposite of what the brain is doing. So despite the fact that we've been trying to copy the computational aspects of the brain for at least 75 years, we still don't seem to be making the progress that we want in terms of having brain-like computing on chip. And so I think there's a reasonable question to ask, which is why, if this approach hasn't worked today, why would it succeed now? And the answer that I like to advocate for has nothing really to do with the great progress that we've made in neuromorphic computing, nothing to do with the progress we've made in device physics. It has everything to do with experimental techniques in neuroscience, right? Biological inspiration has been around for a long time. The question is, have we been able to get the right data out of biology to inspire our systems at the right level of resolution, at the right sort of granularity? And I think that this explosion of tools in neuroscience now, things like serial electron microscopy, volumetric calcium imaging, optogenetics, and these other tools, provide the basis for the first time in history really to exploit, to reveal and then exploit the computations that the brain is doing at the appropriate scale and resolution. So as I said, IARPA is making an investment in this area. I think over the course of the workshop you'll see a number of presentations that span the three sort of different categories that are represented on this slide. And so I'm really excited to see what everyone has to say today and to hear about all the exciting new work that's going on in this field. So thank you.